So this topic is on rates of change of polar functions. And in this section, we will learn ways that we can describe characteristics of the graph of a polar function. So this is something that is very AP specific. Back in honors pre-calculus, we didn't talk about the rates of change of polar functions, but this is a way of us connecting rates of change with functions in rectangular form and how they share the same attributes, but as we switch to the polar coordinate, we have to recognize that there are different rules that we follow for these. So given a polar function r equals f theta, we know that r represents the signed radius of the function. We can use the phrase signed radius because r can be positive or r can also be negative. So as we trace the graph of a polar function, we are interested in whether the graph of r is getting closer to the, that should say pole, that should be pole, the center of the polar coordinate graph, or further from the pole over a given interval. So what is this going to look like? So first, let's take a look at this. We have a polar curve with an inner loop, and it has a maximum radius of 3. I can see that because it's labeled here, and I can see that it extends all the way to the furthest circle out. We have a couple points on here that we'll talk about in a second, but if we notice, if you recall from the last couple of videos, this has vertical symmetry, right? Which means this is going to be a sine curve, some type of sine curve. We're not given the function, but based on that, we know that this will be a, oh, we are given, whoops, it's down here. We have a sine curve, and then this is going to be a limacon with an inner loop because our constant is less than our coefficient. And when that happens, that creates this inner loop that will have a negative radius when the rest of the loop will have a positive radius. So as we extend around this, we're going to take a look at when is the relationship between the radius and the pole increasing and or decreasing. And relationship meaning is the distance. Okay. So if we look at the right side, the left side, it says that when r is equal to f of theta is positive and increasing. And we also have another statement that says when r equals f of theta is negative and decreasing. When this happens, that means the distance between r equals f of theta and the pole is increasing. And this is when, if you think back to rectangular, if the function was positive and increasing, we would say that the rate of change was increasing. And if it was negative, or if it was negative and decreasing, we would say that the rate of change is decreasing. All right. So this is going to have the same attribute as rectangular. This is when the function itself and its rate of change have the same sign. So we can think, oh, the function's positive, or the radius is positive, and the radius is increasing. That means the distance from the expression and the pole is also increasing. So if we think about this visually, I have this point here at A. So at point A, I see that the distance from the pole to here is going to be 1. All right. So my radius is still positive, and as I travel through, the distance from the pole is increasing because the radius is positive and the radius is also increasing. Now, when I hit B, the radius or the curve is going to start decreasing because the radius is positive, but now it's getting closer to the pole, which means the radius is decreasing. So the pink, we're still traveling around. We see that the distance from the pole to the expression is getting smaller and smaller and smaller. So that means on this side, r equals f of theta, the distance is increasing as it relates to the pole. And then on this side, for r equals f of theta, the distance from the pole is decreasing. So on the right side, it's because the radius itself is positive and the rate of change is positive, which means these two have the same sign. And then on the left side, the radius is positive, but the rate of change is negative. So that means it will be decreasing. The distance from the pole is decreasing. Okay, and that's what the second part is here. So if r equals f of theta is positive and decreasing, or or r equals f of theta is negative and increasing, the distance between r equals f of theta and the pole is decreasing. And this is when they have opposite signs. When the function is positive, but the rate of change is negative, the distance between r and the pole is decreasing. And this is when they have opposite signs. Okay. So you'll also see multiple choice questions with this, and the suggestion is that we go back to a sinusoidal curve. Okay. Which, if you look at this, you're able to plot this based on transformations. We have a vertical dilation with a scale factor of 2, and then a vertical translation of positive 1, okay? And that's what we see down here is a sketch of this graph. It's this curve, but we drew it in a rectangular coordinate, all right? So we see that sinusoidal curve as opposed to the polar curve that we see on the polar coordinate, okay? So we have a couple, I'm going to erase this so we can see the points. So we have a couple points labeled here. If I look at A, now the radius here is going to be 1, and my angle is going to be 0. So if we go back to our sinusoidal curve, we can see that this is where it's going to start. All right, so down here we see our angles. And then here, the vertical axis will be the radius length. Okay, so at 0, the radius is 1. And then our next point here, the orientation is going to go counterclockwise. And if I look here, I'm on that vertical axis. This is when theta is equal to pi over 2. Okay, and the radius here is going to be 3. So that's my next checkpoint. So at pi over 2, the radius is 3. That will be point B. And if you look at our sinusoidal curve, the radius is represented by how far we are from the horizontal axis, or in this case, we'll call it the x-axis. Okay, point C on here, it looks like we're back at the pole. As I travel counterclockwise, I end up back at the pole at point C, so that means the radius is 0 again, so that will be at 7 pi over 6. Now, this inner loop, we've talked about this a couple times. After you pass the pole, the radius becomes negative. So technically, if I'm thinking negative, if we were to continue around, I would end up at 3 pi over 2. If the radius was positive, I would be out here. But because the radius is negative, my 3 pi over 2 ends up on the inside, or part of this inner loop, which is D. So at 3 pi over 2, this is going to be point D, and it has a radius of -1, which if I look at this inner loop, I can see that it does have a distance of 1 from the pole, all right? So if I were to plot this, if I got rid of some of this in here, if I were to plot this, I would go, the radius is, what was it again? -1. So radius is -1, so I go back -1, and then I open counterclockwise 3 pi over 2, which would be around here. So we end up at this point here. So the negative radius is from here, and then we open up 3 pi over 2 counterclockwise to get to that coordinate. And then as we come around through here, let me see, get rid of some of this. We pass through D, and then we pass the pole again, and then we end up back at A, where we started. So that little section after we pass the pole here, if you notice in our curve, that is this section here. It's just above the x-axis, or 0. Okay, because we cross the pole again, we end up having a positive radius, okay? So from, actually, we'll call this, let's see, we should have more point. We'll call this point E as well, and then when we arrive back to A, we'll call that F, just so we can see. So we'll call this E, and then this will be F, just to kind of finalize it. Okay. So if we think about how these two relate, if I start here, I have my positive radius coming around, and it's increasing from 0 to pi over 2. Same thing happens here. I see that my sinusoidal curve, as I look at the distance from the x-axis to the curve, it's increasing all the way up to b. Now we'll use the pink again to represent that the radius is positive, but now the slope is negative, which means it's decreasing. And I can see that also here. The distance from the x-axis to the curve is positive, but it's decreasing. Then as we pass, we are now negative and we're decreasing. We'll make this the red here. We are negative and we are decreasing here, which means that the distance from the pole to the curve is increasing. Because even though I'm going away, it is negative, so those two have the same sign, therefore the distance is growing. And then this last one, now we are still negative, but we are getting closer to the pole, which means the distance from the curve to the pole is decreasing. And then one last time, this little section here, we are positive and we're increasing, which means that the distance from the pole to the curve is increasing, okay? So that's what we're going to be looking at. And if you want to see it labeled from here, from A to B, the function is increasing. And then from B to, not B to C, but B to D, actually, it is decreasing. And then from D to F, the function is increasing. So again, we think back to our relative extrema, where the rate of change, or the slope, is 0. This is when a function will change from increasing to decreasing. It's the same thing for polar curves. So if I look at this polar curve here, I can see the direction changes. So at B, the curve is changing directions. And then at C, it's changing directions. At D, it's changing directions. And then at C, it's changing directions. Okay, so that's what we want to look for when it's changing. However, it is difficult to see if you're not familiar with polar curves, which is why we redraw it as a sinusoidal curve. And then on the side here, we can see that from 0 to 3, we have a positive radius. And then from 0 to -1, we have a negative radius. All right, so description of f of x, and we're going to use the intervals. F is positive and increasing. We're going to use the points that we had. So f is positive and increasing. We can see that from A to B, f is positive and increasing. So we'll say A to B. Now there is another section where it's positive and increasing from E to F, that very last part. So and E to F. Now we're going to look at when is f positive and decreasing, okay? There's only one interval where it's positive and decreasing, and that's going to be from B to C. When is f negative and increasing? Negative and increasing, this is going to be when it's below the horizontal axis, and that's only happening from D to E. So from D to E, f is negative and increasing. And then the last one is negative and decreasing. That will be from C to D. All right, so in the polar coordinate system, the graph of f becomes f of x is equal to 1 plus 2 sine x, becomes f of theta equals 1 plus 2 sine theta, as shown in the table above. The labeled points A through F correspond to the intervals from example 17. All right, so using example 17, we're going to complete the table. So let's see, interval from A to B. So the interval from A to B in terms of theta is going to be from 0 to pi over 2. And then B to C, we have pi over 2 to 7 pi over 6. C to D is 7 pi over 6 to 3 pi over 2. Whoops, let's write that in inequality notation. And then D, that should say D to E. Sorry about that. D to E will be 3 pi over 2 is less than theta, which is less than 11 pi over 6. And then that should say from E to F, which is also A in our polar graph, will be 11 pi over 6 to 2 pi. All right, so now we are determining, is it positive or negative, and is it increasing or decreasing? So from 0 to pi over 2 and from pi over 2 to 7 pi over 6, r is positive because it is above the x-axis. And then it's also positive from e to f, so we'll go ahead and write that in. Now this curve is negative from 7 pi over 6 to 11 pi over 6 because it's below 0, below the x-axis. So we'll put that negative for both of these intervals. All right, now we'll do increasing versus decreasing. From a to b, we can see that the slope is positive, so r is increasing. From b to c, we see that maximum, therefore the slope is turning around to be negative, so r is decreasing. C to D, the function is still decreasing. D to E, we see that minimum, so it's decreasing before the minimum and it's increasing after the minimum because the slope is positive. And then from E to F, the function is still increasing. So now we can take a look at these two combinations within each interval and determine the distance between F and the, that should say, pole. I guess it depends on what graph you're using. I'm going to just refer back to the pole. Positive and increasing means that the distance is increasing. We have a positive for outputs and positive for slope. From B to C, we see that it's positive and decreasing. Therefore, the distance between F and the pole is decreasing. Negative and decreasing, that means the distance from F to the pole is increasing because they are both negative. Negative and increasing, that means the distance is decreasing. Positive and increasing, that means the distance is increasing. So if you think about these as, all right, we have a positive, we have a positive. If you multiply those together, it's a positive. The next one, we have a positive, we have a positive and decreasing. If you multiply a positive and a negative together, you get a negative, therefore it's decreasing. And then here it was positive, so it's increasing. All right, so what is this going to look like in the context of a question? So it's often helpful to sketch a graph of a given function in rectangular coordinates when attempting to describe the behavior of a polar function. This is true. However, in our previous examples, when we were given a polar sketch, I would stick to that sketch. It's very time consuming to try and convert that to rectangular. However, you are able to if you wish. But with this one, we don't have a sketch. We just have an expression or a polar function. So we just convert it to rectangular for ease. Okay. So consider the graph of the polar function in the polar coordinate system from 0 to 2 pi. Which of the following statements is true about the distance between the point with polar coordinates and the origin, aka or the pole? Okay, so let's read through these first and see what we're trying to look for. The distance is increasing from pi to 5 pi over 3 because f is positive and increasing. The distance is increasing from 5 pi over 3 to 2 pi. Okay, so we need to get a sketch of this to get an idea of what the outputs look like and then also what the rate of change is going to look like. So my first suggestion is let's try let's go back to January. Let's try trig transformations, all right? So let's start with the transformation table. So we are dealing with cosine. So if we think back to cosine, parent function would look like this, okay? So we had our, we'll call it theta, and then we have our outputs, which will be f of theta. Or we'll call it r, how about that? We'll call it r. So our parent function, we went from negative pi over 2, 0, pi over 2, pi. And for cosine, we went from negative 1, 0, positive 1, 0, negative 1. Okay, so let's try transforming these. All right, so if we notice, we have 2 minus 4 cosine theta. If I were to write this in the standard form, I have negative 4 cosine theta plus 2, which means I don't have any horizontal transformations. I only have vertical transformations. There are 2 of them. So we have negative 4r plus 2. Okay, so if I plug in negative 1, I get negative 4 times negative 1, which is 4, plus 2, which is 6. Plug in 0, I get 0 plus 2, which is 2. Plug in 1, I get negative 4 plus 2, which is negative 2. Plug in 0, we get 2 again. Plug in negative 1, we get 4 plus 2, which is 6. All right, so let's try sketching this. So I'm going from negative pi to pi. So I have negative pi over 2, 0, pi over 2, and pi. And then we're going to 6, and we're going to negative 2, so we'll put that like right here. And then I have a 2 here. Okay, so at negative pi, we're at positive 6. Negative pi over 2, we are at 2. And then at 0, we are at negative 2. Pi over 2, we're at 2. And then at pi, we are at 6. Okay, so I have my transformed sketch. However, it does go to 5 pi over 3 and 2 pi. So let's go ahead and follow the periodic curve. So if I go to 3 pi over 2, and then we'll add 2 pi, okay? So that means at 3 pi over 2, we'll be at 2, and then at 2 pi, we'll be at negative 2. Okay, so here is our curve. All right, so really we are working from pi to 2 pi, it looks like. So really I'm only focused on this. So let's see what's happening. So if I think about this problem in the context of the distance of the expression to the pole, I'm looking at, starting at pi, I see that it's here. It's positive, and it looks like because the slope is negative, it's decreasing. So it's positive and decreasing. Okay, now I don't know what this is just yet, where it crosses, which is where it would start to change between positive and negative. But based on the context of the problem, I can go ahead and assume that it's 5 pi over 3. All right, it's all consistent. That's the only point where I don't know where it is. However, if you really wanted to solve for this, where it's crossing the x-axis, this is technically when r is equal to 0, so set it equal to 0. So we have 0 is equal to 2 minus 4 cosine theta. Subtract 2. So I end up with 1/2 is equal to cosine theta. And then on our unit circle, cosine 1/2 will be at pi over 3 and 5 pi over 3. So that means here, this is pi over 3, but that doesn't matter for this problem. But here, this is when theta is equal to 5 pi over 3. So we can easily find out when it crosses the x-axis by setting it equal to 0. And then once we pass 5 pi over 3, I can see that the function is negative and decreasing. Okay, so for this top part here, from pi to 5 pi over 3, the function is positive and it's decreasing. But from 5 pi over 3 to 2 pi, which is here, the function is negative and it's still decreasing. All right, so let's take a look. Part A says that the distance is increasing from pi to 5 pi over 3. That is not true, okay? We can see that it's clearly decreasing here from pi to 5 pi over 3, so we'll get rid of A. The distance, let's look at the second part. It's not quite obvious, but so this is the new material. This is what we are referring back to rectangular. So part A says positive and increasing. It is positive, but it is not increasing. It is decreasing. Okay, so we can mark out A. And then part B says from 5 pi over 3 to 2 pi, so that's the red, f of theta is negative and increasing. Now, it is negative because it's below 0, but it's not increasing. It is decreasing, so it's not B. Part C says, because f of theta is positive from pi to 5 pi over 3, this is true, and it's decreasing, which is also true. All right, so I'm going to say C, but let's check out what D says just to be safe. From 5 pi over 3 to 2 pi, so that'll be the red, f is negative and decreasing. Well, shoot, this is true as well. All right, so the second part for C and D are true, all right, which is why I'm glad I checked. Now let's look at the first part. Part C says the distance is decreasing from pi to 5 pi over 3. So if I look at this, this says positive and decreasing. So I have a positive, and then I also have a negative slope. If I put these together, it means that the distance should be decreasing. A positive times a negative makes a negative, so it should be decreasing. So C would be the true statement. In part D, it says that f is negative and it's decreasing. If I multiply these together, I should get a positive, which is not true, all right? This says decreasing, so that one is not true. So the answer is C. So there's a lot of moving parts going into this. We used a transformation table to graph it. We had to follow the periodic curve in order to extend it to the domain that we are working within. And then we had to check, when is this crossing the pole, right? So there's multiple parts that go on whenever you're trying to solve these. All right, example 19, which is actually the last example. Example 19 says the graph of f of x, which is 3 sine 2x, we're going from 0 to 3 pi over 2, is shown above in the rectangular coordinate system. If the polar function where f of theta equals 3 sine 2 theta is graphed in the polar coordinate system from within the same domain, on which of the following intervals is the distance between the point with the polar coordinate and the origin decreasing? Okay, so if we're thinking decreasing distance, that means it's going to be negative. And to get that negative, we need a positive with a negative, or we need a negative with a positive, all right? Basically, that means I'm going to want positive. I want the curve to be positive and decreasing, or negative and increasing. All right, which in this rectangular form, or this graph, we can go ahead and take a look at that. So from here to here, the curve is positive. And then below, the curve is negative. So now if we look at the curve and its slope, it's increasing from 0 to pi over 4, and then it's decreasing from pi over 4 to 3 pi over 4. We see that minimum, and then it's increasing from 3 pi over 4 to 5 pi over 4, and then it's decreasing from 5 pi over 4 to 3 pi over 2. Okay, so I'm going to use the pink. We'll say that that is increasing. The radius is increasing, and then for the green, we'll say that it's decreasing. Okay, so from 0 to pi over 4, the curve is positive, and it's increasing. Therefore, the radius is increasing because the distance from the horizontal axis to the curve is increasing. And then from pi over 4 to pi over 2, it is decreasing because as we travel down the curve, we are getting closer to the horizontal axis. When we cross at pi over 2, the curve is now negative and the slope is decreasing, so we are getting further from the horizontal axis, aka the pole. And then again, we are switching back. Now it's decreasing because it's negative and the slope is positive. And then from here, the radius is going to be increasing because now it's getting further from the pole or the horizontal axis. And finally, we have it decreasing here, okay? All right, so part A says, which one are we looking for again? Which of the following intervals is the distance between the point and the pole decreasing? So we want the green, decreasing. A says from 0 to pi over 4. Well, from 0 to pi over 4, it's increasing. So it won't be that one. Part B says pi over 2 to 3 pi over 4. Well, from pi over 2 to 3 pi over 4, which is this section here, it is negative, and the slope is decreasing. So negative and decreasing means that the distance from the pole, between the point and the pole, is increasing. So it won't be B. C says from 3 pi over 4 to pi. 3 pi over 4 to pi is going to be this section here. So from 3 pi over 4 to pi, the function is negative, and it's increasing. So we have negative and increasing. And if we multiply those two together, we get negative, which means the distance is decreasing. So the answer is C. For D, it says pi to 5 pi over 4. The distance between the pole and the curve is actually increasing here. All right, that's it for this topic. Hope this video helps.